We are pleased today to have Vincent Baltz giving the general seminar of Laboratoire de Physique des Solides. So the topic is a quite hot and recent topic, which is called Altermagnetism. So Vincent Baltz is a CNRS research director working in a lab called SpinTech. And in fact, he has always been there because he did his PhD when the lab opened. He was for a postdoc in Leeds for 1.5 years, and then he got a position in SpinTech. So his subjects, in fact, have always more or less have something to do with antiferromagnetism, because in his PhD was studying exchange bias with transport. Then, okay, during his postdoc, it was, but not really antiferromagnetism, but using transport again to look at materials. And then he worked first on antiferromagnets, and he's one of the first people in France to have looked at altermagnetism experimentally. So he will give an introductory talk about these new subjects of physics. Thank you.
Well, thank you very much. Thank you very much, André, for the invitation, and thank you to the organizing committee. So I'm super happy to be here because some 20 years ago, during the PhD, I came and did 2 weeks of experiments at the LPS in the group of Jacques Ferré. And I really keep a very good memory of this moment. So that's why it's a kind of a Madeleine de Proust to come back here. So I will talk about altermagnetism. And if you want, we can first discuss this illustration, which to me summarizes the talk. I will do the talk, but we will first discuss this illustration. So if we look at this illustration, we got 2 families of moments. Some are pointing upwards, some are pointing downwards. So we have 2 sublattices. Overall, the sum of all these moments is 0. But what is very specific is that around this moment, you have a moment density, which is anisotropic. For the down moment, it's pointing along y, and for the up moment, for the down moment, it's pointing along x, and for the up moment, it's pointing along y. And this anisotropy is really the hallmark of altermagnetism, because at the end of the day, it means that these 2 sublattices are not equivalent. And we will see that in terms of transport, these 2 sublattices will respond differently. So in terms of transport, it's as if you are dealing with a ferromagnet, because we will see that one sublattice will prevail over the other one. Magnetization is equal to 0, but the transport is completely anisotropic. Before I move on with the presentation, so I will do a general introduction about altermagnetism, and then I will focus on some of the results we obtained on our hallmark altermagnet. And the results I'm going to show have been obtained within an international consortium, Franco-Germano-Czech, and a bit from the UK. So at SpinTech, we mostly did some transport measurements. At CINAM, they grew the samples. In the Czech Republic, they did some thermoelectric transport, plus some theory. And in Germany, they mostly did the theory. And then we have some complementary theory and experiments from these 2 other groups. So I would like to acknowledge all these colleagues because they contributed to the results I'm going to show in the second part of the talk. So I will talk about magnetism, but let's put magnetism aside in this first slide. So here, what is drawn here are 2 atoms, 1 and 2, which are surrounded by these black atoms here. And you see that the way these atoms are surrounded is different. So you have got 2 losanges. One is pointing along x, the other one pointing along y. And because the environment of position 1 and 2 differs, then the filling of some orbitals will be favored compared to others. So even if in this non-magnetic crystal, you've got a lift of the bond degeneracy in the bond structure. It's simply due to the crystal field and to the electronic environment of atoms in position 1 and 2. So on top of this, if we add magnetism, so this checkerboard distribution of spins, but we simply color this diagram, and we end up with a spin-dependent lifting of the bond degeneracy with some openings here and there, hence the name alternated spin splitting, altermagnets, because you alternate the spin splitting when you go along the reciprocal space. So what is really important to understand is that what matters for altermagnetism is this asymmetric environment, depending on where you sit, or in which position you sit. And we will see that this is important later on for the talk. Viewed from the prism of symmetry, an antiferromagnet here on the left-hand side and an altermagnet, they belong to two different symmetry groups. So that's why people didn't want to call this an antiferromagnet or a spin split antiferromagnet, because this would have been misleading. These are two distinct symmetry groups. An antiferromagnet, overall, it doesn't break time reversal symmetry. That's why there is no intrinsic spin physics with an antiferromagnet. And an altermagnet, it breaks time reversal symmetry. And that's why intrinsically you can have access to some spin physics effects. So that's why an altermagnet, it can polarize an electrical current like a ferromagnet, simply because it breaks time reversal symmetry, or it has some lifting of the bonds. And it also combines the advantages of an antiferromagnet, because overall you've got a zero net magnetization, and for some reasons which I will not detail, you can reach terahertz dynamics like in an antiferromagnet. So that's why, as such, people think that in the long-term perspective, altermagnets could be interesting for spintronics applications, because they could replace ferromagnets in application. There is still a long way to go before this happens, but that's a potentiality. Here, I will describe a typical ferromagnetic application, and I will explain why altermagnets could be interesting for this application. So this is a memory, two ferromagnetic layers separated by a non-magnetic layer. And here you've got the flow of electrons, which is split into majority electrons. So those electrons which moment is aligned with the moment of the ferromagnet, and minority moments, which are all the other electrons. So basically here, because those moments are aligned, they won't be much scattered, and the flow of majority electron is very large. So you shunt the current in this channel. The resistance of this memory is small. And if you reverse the magnetization of the ferromagnet, then both channels are equivalently scattered, and in average, the resistance of this device is high. So you can have exactly the same effect that is predicted theoretically for altermagnets. So here you got two altermagnets separated by a non-magnetic layer. On the left-hand side here, the two altermagnets are pointing along the same direction. And on the right-hand side, we reversed the magnetic order parameter of the altermagnet on the right-hand side. And for this configuration, the resistance is small. For this configuration, the resistance is large. I would say that it's as if one sublattice dominates over the other one. So you can do exactly the same reasoning simply by considering one sublattice and not the two sublattices anymore. So this could also well be a memory with zero net magnetization, and which could work in the terahertz regime. So here I've said that we have reversed the order parameter of the altermagnet. But what do we mean when we say order parameter of the altermagnet? So in terms of order parameter, in magnetism, usually we use dipoles, a magnetic moment, that's a vector, so rank 1 tensor. And with dipoles, we used to describe antiferromagnets or anything that has zero net magnetization. So the Néel vector, sum of all the dipole, is equal to 0 in an antiferromagnet. But this description, it falls short when it comes to trying to distinguish between an antiferromagnet and an altermagnet, because in both cases, the sum of the dipoles will be 0. And that's why it's important to go to higher magnetic orders when it comes to describing altermagnets. Higher magnetic orders, So you've got quadrupoles or octupoles. So these higher magnetic orders, they come from the Taylor expansion of the Zeeman energy when you consider an inhomogeneous magnetic field and an inhomogeneous spin density. For an antiferromagnet, all those multipoles are zero. They are all equal to zero. For an altermagnet, some of those high-order multipoles or some components of those high-order multipoles will be non-zero. So this is the example for manganese difluoride. So for manganese difluoride, the rank 1 dipole is equal to 0. Rank 2 is equal to 0, but for symmetry arguments. And some of the octupoles, so rank 3, are non-zero. And basically, with some of these octupoles, they represent the spin density around an atomic position. So here you see that it's anisotropic. The white lobes correspond to a negative spin density, and the orange lobe corresponds to a negative spin density. And we see that in all positions, all those spin densities are aligned in a parallel. So there is a ferroic octupole moment, even if you've got an antiferroic dipole moment. And the magnetic order is the octupole moment for this type of altermagnet. There are other types of altermagnets for which the octupole moment will be 0, and then you got an even higher octupole moment. What I think we can notice is that in this octupole moment, you've got here mu, which is basically it's the multiple density, which is influenced by the electric multipoles. So it can link to what we have seen in some of the first slides, where we said that there is what is important is the electronic environment, the local electronic environment. So this is hidden in this term. And what I find super interesting is that back in 1989, so a long time ago, people were able to measure this anisotropic spin density in manganese difluoride by polarized neutron diffraction. So here's the lines that you see here. So you see manganese atoms in red, fluor atoms in white. I think in this system you got 4.7 μb of moment on each manganese site. And the dashed line and the straight line, they correspond to an excess or to a lack of spin density around this manganese moment. And you clearly see that this is highly anisotropic. So the root of altermagnetism, even if it was not called altermagnetism at that time, was already measured a long time ago. Okay. In this slide, I just want to pause for a minute. We've talked about intrinsic effects, and we haven't talked about extrinsic effects, like, for example, spin-orbit interaction. So now if we introduce spin-orbit interaction, even for an antiferromagnet, we will lift the spin degeneracy between the bonds. So even for an antiferromagnet, it's possible to break time reversal symmetry thanks to spin-orbit coupling, meaning that it's possible to do some spin physics even with an antiferromagnet. Just to make sure, spin-orbit coupling effects are much smaller compared to intrinsic effects. So that's why there is an interest of using altermagnets, because you can have spin splitting as large as hundreds of milli-electron volt, like in ferromagnet. It's huge. Spin-orbit coupling is tens of milli-electron volts maximum. But the point I want to make here is that if at the end of the day, we measure a material with a 0 net magnetization, and we manage to prove in this material that we can do some spin physics, polarize some spins, we will never be sure that we are measuring an altermagnet, because it could well be an antiferromagnet with some spin-orbit coupling. So we need more to evidence altermagnetism. More means you can measure directly with neutrons, what we have seen. Spin harpes, I will show a result of spin harpes from the literature in the next slide. But the general philosophy is that if you want to measure transport only, you need to make sure that the symmetry of the transport or that the phenomena that you are measuring agree with the symmetry that are expected for your material. So one measurement is not sufficient. You need to scan along all the high symmetry axis, etc., etc. So that's what I will show this type of physics in a few slides from now. Harpes. Ouais. So this is a result from Krampasky et al., where they have done some harpes on the left-hand side and spin harpes on the right-hand side for manganese telluride, which is predicted to be an altermagnet. In the harpes signal, so they can measure the bond structure. They see that there is some opening in the bond structure at close to not too far from the center of symmetry. And then with some spin harpes, if they scan in energy, they manage to prove that the spin polarization of one bond is opposite to the spin polarization of the other bond. So they evidence this alternated spin splitting for manganese ditellurite. So it's a direct way to show or to demonstrate altermagnetism in manganese tellurite. So it's very elegant. But this type of measurements are quite complicated. So here, for example, they've used a bulk sample and they cleaved it in situ so that their surface is super clean. So this is one way to do it. And the other way to do it is to fabricate your sample in situ in your spin harpes tool, and then your surface is super clean. Voilà. For our samples, we have tried to do some spin harpes, but we could not grow it in situ, and it's a thin film, so we could not cleave it. So the result was not positive. We did not manage to have this type of super clean signal. Okay, so we've talked about a few altermagnets. I said that manganese difluoride is an altermagnet proven with neutron spin-polarized neutrons. Manganese telluride is another one. And theoreticians, they claim that there are more than 200 altermagnetic materials that exist. Most of them are insulators. So there are some ways to demonstrate altermagnetism, but certainly not through transport or spin-dependent electronic transport. Some of them are semiconductors, like manganese telluride. Some are superconductors, and a few are metallic. And our workhorse material is manganese silicide. Why? So we have some fallacious arguments for grants. It's abundant, it's non-toxic, it's compatible with CMOS. But above all, manganese and silicon are low spin orbit elements. So the idea, remember, we said that if you have some spin orbit coupling, it could well be an antiferromagnet. So here's the fact that the elements have some low spin orbit coupling is an advantage for us, because if we see some spin physics, it means that probably we are dealing with an altermagnet. Again, it won't be sufficient, but this is interesting for us. Here are those who did most of the experiments. So Rafael, who defended in 21, Mina in 23, Javi, who was a postdoc, Colin, who will defend this year, and Corentin, who is now with us for a year. So manganese silicide, it has an hexagonal structure. It's made of several types of manganese. So you've got manganese 3+ on this outer ring, which are non-magnetic. In this inner hexagonal ring, you've got manganese 2+ ions. And among those 6 atoms, only 4 are magnetic, and they form a checkerboard distribution of spins. This top view is a bit misleading because you see here there are two triangles, and those two triangles are not sitting on the same plane. It's a P6-3 symmetry, so it's a screw symmetry. So the material is a bit more complicated than just this 2D view. If it's grown in the form of epitaxial thin films, then all the spins along a diagonal are pointing, say, to the left here and to the right here. It means that I won't have time to discuss into details here, but it means that we break the overall time reversal symmetry for thin films. For bulk, the lattice parameters slightly change, and you see that all the spins are not aligned along a diagonal here, and we recover the time reversal symmetry. So time reversal symmetry is not broken anymore for a bulk manganese silicide. So it means that bulk manganese silicide is antiferromagnetic. It's not altermagnetic, which complicates a bit experiments, because we would have liked to have a bulk altermagnet, which is, for some experiments, easier to measure. So the samples are grown by molecular beam epitaxy in Marseille, by the group of Lisa Michez. Here is a TEM image. So it's grown on silicon 111, and because manganese pumps silicon out of the substrate, when you grow this material, at the interface, you've got MNSI thin film. So this thin film, it's non-magnetic above 30 Kelvin. Below 30 Kelvin, it's a ferromagnet. So below 30 Kelvin, we know that whatever we do might relate to this thin film. This is quite hard to grow because you need to grow it at high temperature. You need to cool at some temperatures. In order to get the altermagnetic phase, we believe that you need to keep a little bit of strain from the substrate here. We will discuss it later on, but we also see that the sample needs to be oxidized, so you need to have some degree gradient of oxidation across the layer. And for a long time, this MBE growth was an exclusivity for the consortium. Now there's a group from China who claims they managed to grow it by sputtering, and some of their results are convincing. The colleagues from Czech Republic and Germany, they also calculated the bond structure of the system. This is the bond structure. It is a bit ugly, but if we focus close to the Fermi level, we see that we have this alternated spin splitting of the bonds. Now, if we look from above at the Fermi level, they can calculate some hotspots of the Berry curvature, which is one of the important signature when it comes to electrical transport. And if you sum over the Berry curvature over all the bonds and over all directions, it's possible to calculate the whole conductivity. So the whole conductivity, it's the transverse conductivity. When you flow a current along, say, direction X, you pick up a voltage drop in the transverse direction, which is directly related to the whole conductivity, which is directly related to the Berry curvature, which is directly related to this alternated spin splitting. So that's what theoreticians predict. And experimentally, if we do a whole cross, so this is a mesoscopic whole cross, tens of microns for the order of magnitude of the sizes. So we flow current along X, we measure the whole voltage in the Y direction, and we end up with a transverse resistivity, which vanishes at 240 Kelvin, which is the nail temp, the critical temperature of this altermagnet. In terms of amplitude, if we take the whole parameters of the best material possible, and if we say that we have a very small magnetization, we never reach this type of amplitude. So it can't be related to a very tiny magnetization that remains in the material. And there remains a tiny magnetization in this material, which we measured by squid. So it's not a collinear magnet. There is a small canting out of plane. And the canting is such that we end up with 0.05 Bohr magneton per unit cell. Trust me, it's small. And it can't explain the large values of anomalous Hall conductivity. We'll see in a few slides that we have some more convincing evidence beyond just trust me. This small magnetization is very useful for us because if we apply a magnetic field, then this small magnetization will be sensitive to this magnetic field. And it is a way for us to reverse the order parameter, to reverse the Snell vector of the material. So if we measure the Hall conductivity, inverse of the Hall resistivity, sorry, inverse of the Hall conductivity, and if we scan the field, you see that we end up with two different values, positive and negative. And it's simply that at around 1 Tesla, we reverse this small magnetization, meaning that we reverse also the Snell vector, so we reverse the order parameter of the material. So basically we apply the symmetry operation. We reverse the symmetry of the system. Voilà, so meaning we can reach at least two levels of transverse resistivity. And in this way, if we apply the field in any direction, it means that we will be also able to rotate the Snell vector along any direction. So it means that here we have a way to probe the symmetry of this Hall response. And remember, trying to match the symmetry of the Hall response with the symmetry that is expected for the material is important to make sure that we are not dealing with an antiferromagnet with some spin orbit coupling. Well, so at this stage, it's a likely altermagnet, but we need more. And more means spotting the local anisotropy at the macroscopic level. So in the next few slides, I won't enter into the details of the results that I'm going to show because we could spend hours to make sure that we understand the very details of the experiments. But I will just give you the step-by-step, what we did step-by-step, the overall philosophy of the measurement. So first thing we did is that we asked a theoretician from Mainz, Helen Gomonai, to try to work out or to try to relate the... Yes. Yes, sure. Yes.
And spin orbit. Then you would have a non-zero Bailey curvature also, and sigma xy would behave the way you show.
It could be possible to have this, maybe not with all, but with some other types of antiferromagnets. Like there's a family manganese 3X, which are chiral antiferromagnets, which also give rise to some hotspots in the Bailey curvature, which also give rise to some anomalous Hall effect. And these ones are antiferromagnets, not altermagnets. They don't belong to the same family.
So not enough to have a staggered moment plus Hall effect.
Yes. Yeah, exactly. At this stage, I would say if I would stop here, I myself wouldn't be convinced that this is an altermagnet. We have other measurements which seem to tell us that, yes, it's an altermagnet. There is a theory which seems to tell us that it's an altermagnet. But ultimately, we need more, and that's what I would like to show in the next few slides here. Voilà. So here, the first thing is to we relied on the theory from a colleague who tried to link the local asymmetry, or the local symmetry, or the symmetry imposed by the local environment. She tried to link this with a macroscopic parameter that we could measure experimentally. So she had a look at the atoms around a given manganese atom, and she worked out the macroscopic energy satisfying the symmetry. She also added some shear deformation, because we have other experiments which tell us that there is some shear deformation. I won't enter into the detail of all this, and I'm not sure I can enter very deeply into the details of all this if I had to, anyway. But basically, she came out with the energetics of the system, and from this, she can minimize the energy, and she can return the trajectory of the Néel vector and the magnetization for any direction of the field. Again, we could spend hours on this, but the general philosophy is that she can provide the trajectory of the Néel vector and the magnetization, whatever the direction of the field we apply. From this, she can link the transverse resistivity to the Néel vector and to the net magnetization. And from this, she can give us a pattern. Again, don't be afraid. I will come step by step on some of these graphs. But basically, she can give us a pattern of the resistivity that we can expect if we scan the field along a given plane in the material. Trust me, we need 6 patterns to make sure that we know what we are doing. I will just give you a few hints. If we look at it from a very wide view, we see that overall, those 5 loops, they look the same, with 4 metastable states. And this loop is slightly different with only 2 metastable states. Okay? So in this case, she did the calculation when those 4 atoms are magnetic and those 2 here are non-magnetic. So this case is very specific because the field is always scanned across these 4 magnetic atoms. The field is scanned, if you look at the plane here, along this plane. Okay. And the Néel vector is always perpendicular to those 4 atoms, meaning that for this particular configuration, the Néel vector is always perpendicular to the field. Néel vector is like that, and your field goes like that. So your Néel vector is always happy because you are in a kind of a flop, spin flop configuration. So that's why you only end up with two different directions, which corresponds to when you have reversed the Néel vector. In all the other cases, the Néel vector, which is supposed to point, which is happy along the perpendicular direction to the field, but because the field is not always perpendicular to the Néel vector, but the Néel vector will flop. I don't know if I'm very clear. So there is a point where the Néel vector will be perpendicular here to the plane. So when it's perpendicular to the plane and when you scan the field in plane, then the Néel vector becomes perpendicular to the magnetic field, and again it's happy. So this type of symmetry that we expect theoretically, it's true for this configuration. The specificity of manganese silicide is that you can have this variant, but you can also have this variant where you have flipped the magnetic versus non-magnetic atoms by 120 degrees. And you can have this variant. So all these three variants are rotated by 120 degrees, one with respect to the other one. Meaning that the calculation that was done is true only for this variant. For this variant, you've got this type of pattern. But if you are measuring the other variant, everything is rotated. And if you are measuring yet the other variant, everything is rotated again by 120 degrees. So this, I would say, symmetry pattern really depends on the variant that you are measuring. In order to spot a single variant, we did some very small hole bars, so down to 100 nanometer wide hole bars. If we do this, we can spot a single variant. So here we are comparing experiments and theory. Theory in a light color and experiment is in a bright color. And we see that it matches satisfactorily. So for this specific hole bar, we are looking at, say, variant number 2. So with these results, we believe that the signal we are measuring really matches the expectation or the symmetry that is expected for the altermagnets that we are measuring. So it's a bit more complicated and less straightforward, but to me, it's a lot more convincing. We have spotted other variants in other hole bars in the same sample, which is yet another confirmation that we are measuring the system that we believe we are measuring. And if we measure a mesoscopic hole bar, we measure the average. We are averaging over all the variants. We also have the proof of this. I'm not detailing this here, but that's what we have. Okay, so I've talked about the anomalous Hall effect, but there are a lot of companion effects, and in particular, you've got the anomalous Nernst effect. So instead of applying a gradient of voltage, you apply a thermal gradient, a gradient of temperature, and again, you should pick up a transverse conductivity, and I would say thermal and electric parameters are linked by the Mott relation. So that's what some colleagues of the consortium did. So they applied a gradient here along X, and they measured the voltage drop along Y. And they also compared with the case when they applied a gradient of voltage, and they measured the voltage drop. So here is the result. On the left-hand side, you've got the thermal coefficients, or the thermal measurement. And on the right-hand side, you've got the transverse conductivity. And the two signals, they match pretty well. So in this system, it's also possible to measure companion effects like thermoelectric effects. Okay, for this system, the last experiment I would like to show relates to spin injection. So this was mostly conducted by some other colleagues at CIC Nanogune in Spain, and Prague, colleagues from Prague. Okay. So basically, just focus on the left-hand side here. So we've got an injector here of manganese silicide, and we pass a current across manganese silicide. This is a typical bond structure of manganese silicide, and you see that if we flow a current along this X direction, then we displace more of red spins than of blue spins, meaning that at the end of the day, we will end up with a spin current along the X direction. If now we reverse the order parameter of manganese silicide, but we reverse the blue and red arrows in the bond structure. So if we flow again a current along Y, we will send a spin-polarized current, but with opposite orientation in this copper layer. And the way to detect the spin injection from manganese silicide is simply to put a permalloy layer on the other side, which will see if those spins are pointing parallel to this permalloy layer or anti-parallel. So experimentally, that's what they have done. They have patterned two lines. So one line of altermagnetic manganese silicide, one line of permalloy, one line of copper. They flow a current in the manganese silicide, which sends a non-local spin current across copper, and then you detect the voltage drop here. And you see clearly a non-local magneto-resistance effect. So at small fields, you reverse the magnetization of the permalloy layer. And at high field, you reverse the order parameter of the altermagnet. And we clearly see that here we've got a magneto-resistance effect, meaning that we indeed injected some spin current in the copper layer. In this symmetry, again, it's a bit technical, but it only works if the current that matters is the one that is sent across the edges here. And what they did is that they, on the left-hand side, they cleaned the edges. On the right-hand side, they didn't clean the edges. And if you don't clean the edges, you've got some redeposition during the patterning, which makes that you fall out short of injecting a current in your system. So the importance of the edges here is crucial. There are other sanity checks where they use the permalloy lateral spin valves to make sure that everything is as it should be. But at least here it's an important demonstration because it really proves that you can inject a spin polarized current from an altermagnet. So when you think of potential application, this is an important step forward. Okay, so now I have two conclusions. So one for manganese silicide and one a general one for altermagnets. So for manganese silicide, I would say it's one of the rare altermagnets which is experimentally available. And for us, at least, it's a reference platform. So to study the mechanism of altermagnetism in general, but also, as I've shown recently, to explore a proof of concept demonstration of not yet magneto-resistance devices, but at least the key working blocks like injection and hopefully soon detection. There's still a lot to understand on this material and a lot to do. We've seen that this material is grown by MBE mostly, at least for us. We have now at SpinTech a tool to sputter deposit or to co-sputter materials at high temperature. So we are progressing in this way to try to grow manganese silicide by sputtering at high temperature for two reasons, because it's the industry compatibility is much better for sputtering compared to MBE, and it's slightly more versatile. So it will allow us to play more with the stoichiometry, for example, of the sample, thickness, etc., etc. There are a lot of systematic studies that we haven't done yet. In particular, something that we think is important is the role of oxygen interstitials. There are some experiments which seem to tell us that oxygen interstitials or interstitials in general are important, and we believe that oxygen might sit in these empty columns, and they could slightly strain these empty columns and could be key for altermagnetism. Again, what I'm saying are very rough hypotheses, but these are stuff that we want to check. Some people claim that it could be interesting to use altermagnets to explore how it is possible to flow superconducting or polarized spin triplets. So we are trying to go in this direction. These are the first devices that we've made. So you've got an altermagnet here and some electrodes where we are using a superconductor, but also some angled ferromagnets to try to inject triplets, polarized triplets. And in particular, with Altermagnet, what is interesting is that along some direction, you've got nodal planes, so it will behave like an antiferromagnet. But along other direction, you've got this spin splitting, so it will behave differently. And that's what we want to see. But that is, well, we are really just at the beginning. Voilà. Plus, there are some simulation, atomistic simulation, in particular of textures in altermagnets. That voilà. So here are some of the directions that we are trying to explore now for this particular material. And second to last slide, general conclusion. So I hope I have convinced you that altermagnets are a distinct class of materials compared to ferromagnets and antiferromagnets. It can give access to new spin physics and possibly to more efficient spintronic devices in the long term. There is still a lot to understand, more materials for sure, because there are only, I mean, you can count on one hand, maybe two, the number of materials that have been experimentally studied. Integration into functional heterostructures, because most of the works study the material, but not what happens at the interface for injection, etc., etc. And there are a lot of other stuffs that people are looking at. Just two examples here. Domains. So here people have imaged directly the domains of manganese telluride using XMCD, so circular dichroism, which is usually used for ferromagnets. But again, here we've got two sublattices, and the two sublattices are not equivalent. So one will respond more than the other one. So even XMCD works for altermagnets. Voilà, so here they clearly see the six-fold symmetry of manganese telluride. And in the consortium, we are starting to have some preliminary results of XMCD on manganese silicide. And then a last word about a super elegant theory, which appeared very recently. It's about 2D van der Waals materials. So a single bilayer of iron, cobalt, gallium, tellurium is an antiferromagnet at room temperature. And if you twist two bilayers, there is I don't like to call it, not a magic angle, but a commensuration angle, where you somehow you create a supercell which has a symmetry, which is the right one for altermagnetism. Nothing to do with the magic angle for twisted graphene. You don't want flat bonds. That's not the idea of behind. But still, that may be something to investigate in the future. Voilà, I will end with this, and thank you for your attention.
Okay, thank you very much. We have time for questions. Who wants to start? Okay. Okay, so maybe, sorry.
Yep, thank you very much, very interesting. I have maybe a fundamental question about kind of the little parameter for the, you define to describe kind of the altermagnetism. Is there a classification of all the altermagnets that might exist with the different order parameter, if I can say this like this, that can be possible?
So there are some papers by mostly by Smeshkal and co-workers where they list I think they list most of the altermagnets because they had a look in some prototypical crystallography base de données, banque de données. Database, voilà, so thank you. And they managed to calculate whether these are the symmetry expected. So D wave, G wave, I wave, etc. D wave meaning that you have 4 lobes in the band structure. G wave 8, etc., etc. So there is a list. I don't know if it's completely exhaustive, but yeah, that exists. I think the question now for them is, so they have classified all the collinear or mostly collinear altermagnets, and they are trying to determine whether you can have some non-collinear altermagnets intrinsically. But I'm not super aware of where it is now.
Okay.
Have you tried magneto-optics on altermagnets?
Yes, not myself, but the group of Eva Szmorenzerova in Prague, and it failed, but I can't remember why, because I'm not sufficiently educated in this field. But they have tried to see if there is some mock signal at different energies. So they've tried.
But you mean manganese silicide?
In manganese silicide. In other materials, I think the Chinese group is reporting something. But other than that, I can't see.
Because a priori it should work.
It should work, right? Yeah. Oui.
I can shout. Yeah, I'm just wondering about the thermodynamics of these, even if you just take the altermagnet, is there statistical mechanics of these objects? So can you calculate TC and exponents? I don't know. If you can't measure the order parameter, it's difficult, but at least numerically, has this been done?
I suppose for some antiferromagnet, for some altermagnets, it has been done. For manganese silicide, it's quite difficult because people don't agree yet on the exchange parameters. Voilà, so it hasn't been done for manganese silicide. For the other ones, I couldn't say.
But it should be like the statistical mechanics of an antiferromagnet.
Yes. Yeah.
So once you know the exchange couplings and so on, you can run your favorite tool.
Ouais. But this hasn't been done.
I don't understand what makes it different from an antiferromagnet.
It's
The symmetry.
No. So sorry. So Anu was sort of emphasizing a question, and I was saying if there is no magnetism there, you don't have altermagnet, as one would guess. So yeah, and then she replied. She said, "Yeah, but there is the anisotropy of the environment." And I would say that this reflects the band structure in a way.
Yes, yeah, absolutely. Right, it's directly related. Right. The naming, I understand that the naming can be misleading because and some in the community try to create a false debate about whether altermagnets are real or the naming is okay or not. I would say what is important to understand is that the symmetry, in terms of symmetry groups, what we call antiferromagnets, conventional antiferromagnets, and those altermagnets, they belong to two distinct symmetry groups. So they can't be named in the same way, otherwise it's also misleading. Some people try to say that an altermagnet is a spin-split antiferromagnet, but it would be misleading because it would infer that they belong to the same symmetry group, which is not the case. And if we only look at the bond structure, we could also say that it's a zero magnetization ferromagnet because it has some spin splitting. So I would say when it comes to trying to find the same word to describe a magnetic property and the transport property, that's where we fail. So naming a ferromagnet, and an antiferromagnet is also not ideal when it comes to discussing transport.
Other questions? No? So, okay. Attends encore une.
Sorry, it was about the switching mechanism where you are switching the magnetism. It seems that it was about 1 Tesla.
Yes.
It sounds big. My question is, with other type of altermagnet, might it be very slower and then usable? Or if you had, for example, a magnetism with spin-orbit coupling, will it be reduced, the spin flick?
But this all depends on the anisotropy or other energetics term in the system. For manganese telluride, it's 6 Tesla, so even larger. Ruthenium dioxide also even larger. I would think you can find anything. It's like I would say it's the same question as what is a spin flop field of an antiferromagnet. Usually people say it's very large, but you can find antiferromagnets where the spin flop field is super small. So it really depends on the internal energies at stake in the system.
Maybe a small question. Thank you very much for the nice presentation. So there is this octupole order parameter. Do we see it in the far field if you measure the field distribution around the sort of single crystal of this altermagnet? Do you expect to see an octupolar magnetic field pattern then, or is just local, the nanoscale?
Tough one.
So this is Andreev paper.
Right.
There is a paper by Andreev in the 90s where they say you can have an antiferromagnet which has no dipole moment, but it can have a quadrupole moment. And then they found a crystal, and then they measured with a squid the stray field of this single crystal, and they found the fourfold symmetry.
Okay.
UPL 96 or something like that. But okay, it was an antiferromagnet, not I don't remember the compound it was.
Okay. So from this point of view, is there a difference between altermagnet and antiferromagnet if they have similar stray fields?
In terms of magnetism, if it only relates to magnetism and magnetostatics, there shouldn't be any difference, I would say, a priori.
I don't understand, because you said that for antiferromagnets, there was no multipolar moment.
Oui, but I don't know the paper by Andreev, but apparently it's possible to measure something. For an
okay, I have to look what is the compound.
Maybe it's at the boundary where you break.
Non, c'est un dipôle, ça te fait un champ comme ça. Si tu as un quadrupôle, ça te fait un champ comme ça.
Mais il a dit que...
Ouais, pour les antiferros, ouais, a priori for antiferromagnets, you shouldn't have multiple moments.
Il y a quelque chose.
Okay, it's an old paper, so I don't know what is the compound and how it's classified now.
I thought for altermagnet, in the speed wave spectrum, you have also a speed splitting. I mean, anisotropic speed splitting. The speed wave spectrum. But
Yes.
So it's different from the antiferromagnet, even for purely the magnetic part.
True.
Are there altermagnetic
True, but
insulators?
Oui, bien sûr.
Yeah. There are some insulators. These ones are not insulators, but there are some insulators. Manganese difluoride is an insulator, for example. Hematite is now classified as an altermagnet, and it's an insulator.
How do you characterize it?
Alors, we don't, but those who are working on this, I would say these things are so I'm not a specialist of neutrons, but they are trying to look into neutron techniques, I think, to characterize these spin waves and this opening.
The imaging you were showing for manganese telluride by combined XMLD and XMCD, it has been performed on Fa203. And so they have also XMCD and XMLD, and they can get the orientation of a Néel vector everywhere.
Voilà, but they don't see for the spin wave spectra to try to evidence the splitting of the waves. I think there are people who have a lot of ideas with neutrons. There's Dalila, I can't remember her name.
Bunula.
Voilà, wait, and Paul McClarty.
There's no, for example, thermal transport or something like that.
Ouais. Perhaps. Ouais.
J'en ai encore une. Regarding your whole measurements, so you were showing, okay, you fabricate a whole course, you measure, and then you get a whole signal, and then if you apply the big field to reverse the Néel vector, you obtain the opposite. But okay, it's more difficult to make experimentally, but I can think of it. If you make a whole course with many more contacts, and then you can measure with a current in many directions, not so many, then I would expect that you see some reversals of the whole effect as a function of the angle. So have you tried this or?
We've tried something like this, but at the end of the day, I think we were not entirely sure in terms of symmetry, we didn't see much, and the other doubt we had, is about the current density that we are flowing along each branch, to make sure that it is homogeneous, because you always have some inhomogeneities when patterning. I agree with you that it should not affect the symmetry of the signal. We've tried something like this, but not conclusive.
No more questions, no? Okay, so we thank the speaker again.
Thank you.
So he will be in the lab for some hours, and